All right, next thing I want to talk about is the fundamental counting principles. So in the previous lecture, we talked a little bit about counting using tree diagrams, counting by like finding a pattern, right? Counting by just kind of visualizing a tree diagram, and also just basic counting, like listing out all the possibilities and then counting them up. In this lecture, I want to talk about what's called the fundamental counting principle, and just to sort of build up our intuition for this and give us some motivation for what's coming next. Let me zoom in a little. Let's look at this example. It says, suppose we want to add some plants to a garden, and there are 6 species of trees, 4 species of vines, and 8 species of ground cover to choose from. If we choose 1 tree, 1 vine, and 1 ground cover, how many different combinations of plants can we put in our garden? Okay. So we could actually draw out the tree diagram here if we wanted to, right? So we have six species of trees to choose from. So the very first choice I make is going to be, my tree, I guess. So I can say 1, 2, 3, 4, 5, 6. So I have 6 different trees. Now, having made my choice of tree, I need to choose a vine, and there are 4 different vines that I could choose from. So each of these is going to have 4 branches coming off of it. So I'm not going to draw the entire tree because that's going to get quite tedious, right? But 1, 2, 3, 4. And then each of those, and actually let me do one down here because I'll have a little bit more room. 1, 2, 3, 4. Right? But each of these things is going to have 4 different possibilities coming off of it. And then each of these, so now I've chosen my tree, I've chosen my vine, and I now need to choose my ground cover. And there are 8 species of ground cover that I can choose from. So each of these is going to now have 8 branches coming off of it. 1, 2, 3, 4, 5, 6, 7, 8. Right? And I haven't drawn the whole tree, but you can kind of imagine, like, each of these is going to have 4 branches coming off of it, and then each of those branches is going to have 8 branches coming off of it. And so if you were trying to think of what's the total number of different combinations, well, it would be 6 times 4 would get you to the second row, so that's 24. And then 24 times 8 would get you to the third row, right? So we say 6 times 4 times 8. Right? So 6 times 4 times 8, that's going to be the total number of branches. That's 192 branches. Okay? This is what's called the fundamental counting principle. So you may have noticed from the previous lecture, as well as from this previous example, that many of these kinds of counting problems have the following pattern. Some first thing happens in A number of ways, a second thing happens in B number of ways, a third thing happens in C number of ways, and so forth. And then if you want to find the total number of possible outcomes in such situations, it just ends up being A times B times C, and so forth. Right? And that's what's called the fundamental counting principle. So if we want to perform a series of tasks, and the first task can be done in A ways, the second task can be done in B ways, the third task can be done in C ways, and so forth, then all the tasks can be done in A times B times C, and so forth ways. So here's an example. The Engineers Without Borders chapter, this is similar to an example from the previous lecture, but the Engineers Without Borders chapter on your campus is raising money. They're going to select 1 fundraiser for the fall semester and 1 fundraiser for the spring semester. The possible fundraisers are an online auction, air hockey tournament, themed road race, and karaoke night. In how many ways can they select the fundraisers if they don't do the same fundraiser twice? Well, we actually answered this exact problem. So this is exactly the same as lecture 21, example 2, right? Here we answered it by listing out all the possibilities. Here's another way that we could do it. We could say, well, first they're going to choose the fundraiser for the fall semester. Okay, so for the fall semester, how many possibilities do they have? Well, they have 4 possibilities. They have an online auction, an air hockey tournament, a themed road race, and a karaoke night. So there are 4 options for their first fundraiser. Now, they're not going to do the same fundraiser twice in a row. So if they have 4 options for the first fundraiser, then that means they're only going to have 3 options for the second fundraiser. Okay? Because they can't do the same fundraiser twice. That comes out to 12. Right? 12 different fundraisers. So this was the number of ways to choose the first fundraiser. So number of ways for first fundraiser. And this was the number of ways that they could choose the second fundraiser. So for a second fundraiser. Or another number of options, I guess. We could say options. That would make more sense. Number of options for the first fundraiser, number of options for the second fundraiser. Okay? So so there's that. And notice that we did come up with the same answer, but in a different way. And this way, I think you'll agree, was much quicker and nicer and easier. Okay? So let's practice applying that a little bit more. It says, in how many ways can 4 coins be flipped? Goodness gracious, we did something similar, right? In the previous lecture, we said, in how many ways can 3 coins be flipped? And it required us to draw out this tree diagram, right? Now we're going to do 4 coins, and it's going to take us a lot less space. Why? Well, because how many ways can we flip the first coin? Well, there are 2 possible outcomes, right? Heads or tails. And how many ways can we flip the second coin? Well, again, it's 2, right? Because heads or tails. In how many ways can we flip the third coin? 2, heads or tails. And in how many ways can we flip the fourth coin? 2, heads or tails. So it's just 2 times 2 times 2 times 2. And that's going to be 16. So 16 different possible outcomes. Okay? In how many ways can 3 dice, red, green, and blue, be rolled? Well, what are the possible outcomes for the red die? Well, it would be 6, right? There are 6 possible outcomes for the red die. How many outcomes are there for the green die? 6. And how many outcomes for the blue? 6. So it's 6 times 6 times 6, which I think is 216. Yeah, 216. That's 216 different possibilities there. Okay, here's another example. Many restaurants in your city are participating in Restaurant Week, when they will offer a 4-course, fixed-price menu. Patrons will order a complete meal consisting of an appetizer, soup, entree, and dessert. Okay, so those are the 4 courses: appetizer, soup, entree, dessert. One restaurant offers 4 appetizer choices, 3 soup choices, 6 entree choices, and 5 dessert choices. How many different complete meals are possible? Well, the number of complete meals possible is going to be the number of ways that you can choose the appetizer times the number of ways you can choose the soup times the number of ways you can choose the entree times the number of ways you can choose the dessert. There were 4 options for the appetizer, 3 options for the soup, 6 options for the entree, and 5 options for the dessert. So 4 times 3 times 6 times 5 is 360, right? 360 different options. Okay, so that's the fundamental counting principle. That's how it works. Now, something that we've kind of been doing that I think we should give it a formal name is this. So a useful technique for applying the fundamental counting principle, FCP for short, is to draw a series of blank spaces to keep track of the number of ways to do each task. And we call such a figure a slot diagram. So in the homework, you might be asked to draw a slot diagram to answer this problem. They're basically just asking you to do what we did up here, but just draw out a slot for each of the choices that you have to make. So I'll show you an example. So number 5 here says, to open your locker at the fitness center, you must enter 5 digits in order from the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many different keypad patterns are possible if any digits can be used in any position and repetition of digits is allowed? Okay, let's see. So we need 5 digits. So we need to choose 5 digits. So I'm going to go ahead and write out 5 blanks. And I know that ultimately I'm going to multiply all those numbers together. I need to come back and fill these in now, though. So we need to choose, to go into these blanks, we need to choose digits from the set 0 through 9. Sorry. But the question is, how many different ways can we do that, right? So how many ways can we choose the first digit? Well, there are 10 digits here to choose from. If you add 0, so if you count up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 10. 10 digits, right? So there are 10 possibilities for the first number in the code. And then it says repetition of digits is allowed. So we can reuse that digit that we chose for the first one. So there are still going to be 10 possible digits for the second number, and 10 for the third, 10 for the fourth, and 10 for the fifth. So that comes out to, well, it's going to be 1 with 5 zeros behind it, right? So I think that's 100,000. 100,000 possible patterns. Okay? Now part B is the same scenario, but it says the digit 0 cannot be used as the first digit, but otherwise any digit can be used in any position, and again repetition is allowed. So 2, 3, 4, 5. Okay, so for the first digit it says 0 can't be used for the first digit, but you can use any of the other numbers 1 through 9. So there are 9 possibilities for that first digit. Okay, but then the other digits you can use repetition. Okay, I'm sorry, my dogs. Sorry, my dogs were going crazy. They wanted out. So anyway, okay, so 9 choices for the first digit. The second digit can be any of these numbers, though. All right, so that's there are 10 possibilities there. And then the third can be anything, fourth can be anything, fifth can be anything. So it's going to be 9 times 10 times 10 times 10 times 10. That, I think, is going to come out to 90,000, right? Okay. And then one more. So again, same scenario, but this time any digits can be used in any position, but repetition is not allowed. Repetition is not allowed. So once you use like the number 7, you can't use the number 7 again, right, in your 5-digit code. So 2, 3, 4, 5. Let's think this through. So for the first digit, any digits can be used in any position. So you can use any of these numbers, 0 through 9. So that's 10 possibilities there. Okay. For the second number in the code, you can use any number except not the one you put in the first place, because repetition is not allowed, right? So if we had 10 possibilities for the first number, there are only 9 possibilities left for the second number. And then if there are only 9 possibilities left for the second number, then there's only going to be 8 possibilities left for the third one. And then there's only going to be 7 possibilities left for the fourth one. And then there's only going to be 6 possibilities left for the fifth one. So let's see how many that is. 10 times 9 times 8 times 7 times 6 is 30,240. Ooh, so you can see when you don't allow repetition, the number of possibilities is reduced dramatically, right? You have like less than a third of the total number of possibilities that you had here in part A, right? Which is pretty cool. So, but that's that. These are called slot diagrams, and slot diagrams are very useful for counting things. And just generally speaking, right, fundamental accounting principle, very important, very helpful. And that'll do it for that section. So again, a really short one.